Welcome class. We are going to have one more laboratory. This time the laboratory for projectile motion in 2D. Basically, we are going to apply what we learned in the previous laboratory for vectors in 2 dimensions and use the kinematic equation of motion. These equations are obtained using Newton's law, and to simplify the description of motion, we are going to summarize in 6 basic equations. As you can see, you can have only 3 equations. One that describes the position in X, I'm going to use color blue, and from 4 to 6, one that is going to describe the vertical motion, or in Y. Also, as you can see, I'm going to have in my axis right now simulating shuttling from one canyon, something similar you are going to be using during this laboratory. But it's here when you need to start to pay attention in the physical thing. The first thing, whenever you try to describe a motion, is your reference frame. You always need to set up your reference frame. In this case, I'm going to set up my reference frame with respect to the floor. So this is going to be my position Y0. And from here, horizontal, I'm going to assign positive values and positive values. If I have in the opposite direction, that's going to be negative value. So I already set up my reference frames in this point. As you can see, for a projectile motion, we are going to have one cannonball moving, and it's going to be changing the velocities constantly. Any change in velocity we describe is defined like acceleration. So in this case, what is going to make, for example, this child to change the initial velocity? Acceleration. What acceleration? Gravity. Gravity is constantly changing the direction of the velocity, direction down. So I'm going to write here, so we need to keep always that the acceleration is going to be constant all the time during this kind of trajectories on the surface of any planet, or any surface of planet. Okay, let's try to give you an example how to use this kind of equation and make the analysis, so you can simplify those equations with something that you can figure it out. For example, if I take the cannonball, the shooting is not going to start here. What is going to happen here is something that we are going to make an analysis later. So let's focus when your projectile is directly under the acceleration of gravity. So the other way, in later chapters we are going to study momentum and then see what is happening inside the canyon. So at this moment we can use velocity naught, or you can use velocity initial, the very first instant that is in the air. So nothing is holding. So all this equation is when they are going to be equation. So we need to pay attention that my position initial, because I assign my reference point here, can be 0. So we already have one data here. So also, you can use a regular ruler and you can measure what is going to be with respect to reference, the position of the ball. Usually we measure with respect to the center of mass, that is going to be the center, approximately the center of the object to end this. But you can use, for little mistakes, don't worry, you can use the first part of the ball. So it's a very little mistake that we can simplify or carry all the way. So we have one way to obtain Y initial. So let's see. So that means that I have an X initial and a Y initial from only that little analysis in this moment. What I know in this point, the velocity initial, I have no idea. So it's exactly what we need to discover. What's going on? What is that initial velocity that is going to be? Okay, what is happening? Only we know the direction, the angle that is motion, because it's going to be straight with the angle. It's something that you can take your protractor and you can measure the same angle that you have for your canyon, taking in the reference, with respect to the ground, or you can take the reference here, and you can extend and measure exactly the initial angle or your velocity. Okay, suppose that we have three data: initial angle, vertical position, horizontal position. This can be assigned 0 to simplify your data. And what about in this point? In this point, we don't know too much, but we need to learn to start to split your velocities in components. You already studied in class that vectors can be split in components to work and simplify this. So using x, I can find, for example, make the component velocity initial in x. And in blue, I'm going to see a project in this board. I can use this part or this part. In fact, I'm going to use this. This is my velocity initial component in y. So you can use this component or the total velocity initial or the components. Let's see what happened an instant later, at any instant. We are going to have a velocity in x, 1. And also, we are going to have a velocity 1 in y. Let's see what is happening here. We know that the acceleration is always acting in this direction. So, in fact, I switch your colors. Okay, never mind for that. So, you can see that the velocity, the component of the velocity in y is smaller and smaller. Why? Because acceleration in y, the gravity, is only affecting that component, so it's making this smaller. So when we reach the top, so what happened in that moment? If I try to make in common components, I'm going to split here. Velocity at the top. We no longer have components in y because the velocity is one value that we already know. In the maximal point of a projectile trajectory, the velocity in y equals 0. We don't have velocity in y in that. So, and what happened here in x? As you can see, it's the same, it's the same. If we neglect the friction created from the air for short trajectory in a controlled environment like the laboratory, if we don't have too strong air conditioner, okay, we can consider this is going to be constant. So we perfectly know from that, in this point, what is the velocity at the top, because it's going to be exactly the same value of the velocity initial in x. Okay, one instant later, what is going to happen? Okay, I'm going to split in components. Velocity, let's call 0.2 in y. You can see we have a little component. And velocity in x. This is going to be exactly the same value because we are neglecting. Nothing is affecting in x to change that velocity. That's a constant velocity in x. But the change is going to be in y. Why? Acceleration of gravity. Check. We define again acceleration as a change in velocity with respect to time. Finally, I'm going to draw this velocity in the position 3 in y. I already know that this is going to be constant, velocity 3 in x, going to have the same value all the time. And to find the velocity of the impact, you can see it's going to be bigger because we don't have the same level. In fact, if we put exactly at the same level, one with respect to the other, the magnitude of one velocity is going to be exactly the magnitude of the other velocity. But not is going to be the direction. Why? Because we are going to have a change in the velocity in y. Where it comes from that change? The acceleration of gravity. And finally, we have this. It's going to be velocity in x, final position, and this is going to be my velocity in y final. So it's going to be the biggest, even bigger than the original. Why? Because it's in a different port. Another interesting, okay. Now, how we can start to simplify all these equations to identify the values. That's probably the most difficult part in this laboratory. We have 6 kinematic equations, and we have another extra that is for one special case when we have the y initial is going to be exactly y final. So you can find with that the range of values. But that's something that is going to be simple. How to simplify that? I mentioned if you carefully measure and try to make observation, we are going to have data. Let's see if we can find an extra time that we are going to use. Clock. You are going to have, with your timer, you can use your cell phone to try to check, or the TA can provide with a chronometer that's going to be more precision. Let's see. If we perfectly synchronize our clock, time in this moment is going to be time 0. Okay? And what position and velocity is going to be 0. Let's only try to see. If we try to find the position in the horizontal x, in this very instant, let's see. Let's try always one equation at a time. So, x is the value that we want to know. X initial, we already know, define that is 0. We make this 0. Time is time 0. And second time is going to affect, it doesn't matter that the acceleration next, in fact, we don't have, the acceleration next is also 0. It doesn't exist. So anything times 0, 0. So my position in that instant is going to be 0. Perfect. What about y? Y, you can see in this instant, y initial is something that you measure. We have this value. The time, because we just start in that instant, is 0. 0 times any number is going to give me 0. Again, the same. Time in that exactly moment is going to give me 0. So we are going to have the position in that, for this instant, is going to be the y initial. So we have already the coordinates for, with respect to reference frame, this object. But what about the initial velocity? Okay, let's see. If we try to find the initial velocity in this instant, then let's see, velocity in x. Do we know the initial velocity in x? We have no idea. Acceleration in x, we know is 0, so we have no idea. Probably it's not a good idea to use this one. Let's go for another one. Keep changing your equation with the values that you have. That is the best way, and canceling. It's going to simplify. Velocity in y. The time for that instant is 0. Okay, so velocity in y we know is going to be equal to the velocity initial in y. Something that we don't have. So directly we cannot find this equation from this position. Let's try to see if we can use any other equation to find. For example, you can measure the total time that your projectile is in the air. That is going to give me an extra information. Let's focus in this point. Okay, you were careful, taking all your time, so you know the final time. Let's focus and find the values here. Position that we have in that instant in x, you can take your ruler, a big ruler, and measure exactly something that you can do perfectly. So we know the final position. What was the length? Initial, we make this 0. Velocity initial in x, we have no idea. That is my question mark. The total time that was flying is something that we have. Okay. Acceleration in in x, we don't have. We neglect friction of air. We make this component 0. So from that, I can obtain here x final, I know. X initial, 0. Plus velocity initial in x, I have no idea. And the total time flying, I know the total time flying. Okay, so I have two values that I know, and I can find using a little bit algebra. So we have this, we know this, and we can find velocity initial in x. From that velocity initial in x, what does it mean? We can start to introduce in other values, because we already saw that the velocity initial in x is going to be constant in every single point that you want to know. Okay, that looks like to be great, good. Okay, what about the velocity, the position in y? If we can obtain something information from that, let's see. In this point, what is the y? And I'm going to raise this, so I'm going to have more time to discuss. Y final equal, I'm going to use equation number 4. Y initial plus velocity initial in y time plus 1/2 acceleration of time squared. Oh, something that I put not here. That equation. Okay, let's see. Y initial, I know the y initial. Y final is 0. I already know that value. 0. Velocity initial in y, I have no idea. Total time that was flying, yes, is something that I can find. Acceleration in y. We know that the acceleration in y is the gravity. Also, pay attention here. It's pointing in that direction. So it's going to give me a negative value, because this is going to be gravity. Total time that was flying, yes. So basically, from that, I can find also the velocity initial in y. So it's going to be very important. Let's see this. If we can use, I have 0 equal y initial, whatever is that value, velocity initial in y, time minus 1/2 of gravity, time squared. I have everything except this. With a little bit of algebra, and you can use negative y initial, it's negative, positive, 1/2 gravity time squared equal velocity initial in y time. I still have time here. It's in a multiplication, it's in a division. There is one of many different ways that you can find, for example, velocity initial in y. Because you already know every single number, you can find that velocity. What does it mean? That we already know this value and we know this value. This is going to be important. We know also another value, the velocity at the top. We already know that the velocity in y in that point is 0. From the previous result, we found that velocity in the top is going to be the velocity in x. You need to make this kind of analysis, start to cancel things that you don't know, in order to find different values. That's basically, use a little bit of the algebra. The TAs are going to help you with that algebra, so don't feel afraid. Use previous knowledge. So I hope with that we can start the laboratory and you enjoy this activity that is very interactive. So, good. Have a good class.